Hey everybody, this is Chris McClure again, and we are going to go ahead and get started with some new material to get the semester started. So I realize that some of you are still getting your textbooks, let alone have not yet gotten registered with the My Math Lab and stuff. So keep working on that. But let's go ahead and get started with a presentation of some material. And so we're going to go ahead and start talking about the material in chapter 12, where we're going to be discussing vectors. All right, so let me go ahead and get my pen out and going, and I'm going to go ahead and choose green because I just like green today. All right, as of right now, it's Thursday evening, May 23rd, and I'm still sitting in my lodging room at Fort Jackson, South Carolina. I'll be leaving tomorrow and starting my travel homeward. I'll be spending the night in Knoxville, Tennessee. I have a meeting with someone there tomorrow evening. Then I'll be on the second leg of my journey home, headed to Peoria, Illinois, and visiting someone there. And then I'll be home on Sunday. So I'll be enjoying the Memorial Day holiday, taking part in ceremonies with the American Legion and parade and stuff and Ames. Then I'll be back with you guys on Tuesday of next week in person. Looking forward to it. Meanwhile, let's go ahead and turn our attention to the material in section 12.1, where we're going to talk about this quantity called a vector. And in particular, we're going to be paying attention to vectors in 2 dimensions on the plane. And then the next time that we meet, which I plan to record a lecture tomorrow, meaning Friday evening, we'll talk about vectors in 3 dimensions as well. But once you understand vectors in 2 dimensions, and 3 dimensions is an easy extension of that idea. Now, here's the idea behind a vector. A vector is kind of like a quantity that has a direction and a magnitude. So kind of imagine this raft as it floats down a river. So you notice that, if you were to use some sort of arrow to indicate your speed and direction, you might have your speed and direction indicated by this arrow right here, where you see the letter A. But then as your raft approaches the rock, it's going to slow down a little bit and change direction. So notice that this arrow is pointing in a different direction, pointing in the direction that this raft is now going, and the arrow is a little bit shorter, indicating that the speed is less. And then over here to the right, the raft has gone beyond the rock and has picked up speed again and going in the same direction as you were way back here to the left. So the arrow is pointing in the same direction and has the same length. All right, so you can kind of think about that arrow as indicating vector. Velocity. Velocity is a vector quantity which incorporates speed and direction. All right, moving along here. Now, we use vectors a lot. And in fact, a lot of you have already taken some sort of physics and or engineering classes where you've been working with vectors already. But if you have never taken a hardcore science class, you probably are not quite familiar with vectors, and that's okay. We use vectors a lot in the sciences and engineering to indicate all kinds of things. For example, the direction and magnitude of an electrical field between a positive and negative element, or the velocity of air going around an airfoil, like you see here. Or, hey, elementary particles in a bubble chamber. See these little tracks. Well, you can think about these tracks as the path of these elementary particles, and all along that path you can think about little vectors indicating the speed and direction of those particles. All right, so here is your vector here. It's basically an arrow where you have a tail down here where you see the letter P, and you have the head at Q. And your vector is going to go from the tail to the head with a certain length, which indicates the magnitude of your vector, and the direction. All right. Now, here is one way of indicating your vector. This is the vector that goes from point P to point Q with a little arrow over the top. All right. Now, you could have two vectors that are exactly equal to each other, even though they might be in two different positions, as long as they have the same magnitude, meaning the same geometric length, and the same direction. If they have the same length and the same direction, the two vectors will be the same. So here, U and V are probably similar, if not exactly the same, because they have the same length and the same direction. But if U and V were two different directions and or two different lengths, then the two vectors would be different. Okay? Okay. By the way, make sure that when you write down the name of a vector that you're using an arrowhead over the top to indicate that that creature that you just wrote down was actually a vector. All right, so here are some important summaries regarding vectors. Vectors are quantities that have both length, also called magnitude, and direction, so length and magnitude. Two vectors are equal if they have the same magnitude and direction. Quantities having magnitude but no direction are called scalars. All right, so you could have the number 2, that's a scalar, and you can have a vector u, or pq. Both of these are vectors. Scalars are not the same as vectors. Scaling factors is another way of thinking about scalars. Scalars think about them as maybe real numbers that you can actually combine with vectors in order to scale the vector to adjust the length of the vector. All right. Now, here's one interesting vector called the zero vector. Now, the zero vector it's a vector. It has a magnitude of 0, but no particular direction. So it seems kind of weird, but it plays an important role in the algebra of vectors. All right. Now, you could have a vector v. Let me see the black v vector down here. And then you can scale it by multiplying vector v by some scalar, like 3. And when you multiply it by the scalar 3, what you do is you have a new vector that is 3 times as long as the vector v, but pointing in the same direction. Or if you multiply by -2, -2v, it's the same direction except in the opposite direction as vector v, and has a length that's 2 times as much as v. So it's twice as long in the opposite direction. That's what -2 times v does for the vector v. Multiply by a number that's smaller than 1, then you'll have a vector that has a smaller magnitude. 1/2 v is a vector that points in the direction of v, but half as long. It has half the magnitude. Okay? All right, so generally speaking, we have a scalar c and a vector v. Notice that the vector v is written in boldface here. We use boldface to indicate vectors versus scalar c, which is not bold. That's how you can tell them apart. Now, you multiply scalar c times vector v. The result is a new vector with the same direction, but a magnitude that is whatever the absolute value of c is multiplied by the magnitude of v. Now, it'll point in the same direction of v if c is a positive number. If c is negative, it'll point in the opposite direction. By the way, if you have two vectors that are maybe of different lengths but in the same direction, in other words, if one is a scalar multiple of the other, then we say that the two vectors are parallel. So you might have vector v here. All right, you might have 2v. V and 2v are parallel with each other. And so is negative 2v. They're all parallel with each other. Any multiple of vector v is parallel to v because they point in the same direction or in opposite directions of each other. Scalar multiples of each other. All right, let's take a look at example number 1, and you'll find this on page 779, at least page 779 of the original hard copy textbook. I'm not sure about the page numbering for this special edition that they're selling in the Ankeny bookstore. I haven't gotten there yet, and I don't have a copy of it with me. So when I reference page numbers, it's in the big textbook. All right, example number 1. Now, what you need to be doing is referencing the figure 12.6a and b in order to see what's going on here. So we have a vector u and a vector v, and what they're asking us to do is to, with relation to u and v, is to figure out a way of expressing the vector that goes from p to q, and I'll show you that in a minute. The vector that goes from q to p, the vector that goes from q to r, and the vector that goes from r to s. Let's go ahead and take a look at what's going on here. This is the picture that we're supposed to be referencing here. We've got a vector u here and a vector v here. The first one that they want us to look at is the vector that goes from p to q. Now, here's p right here, and here's q. So the vector that goes from p to q is this guy right here. That's pq. Now, using u and v, how can we write pq in terms of u and v? Well, look, if you were just to take the vector u and compare that to the vector that goes from p to q, they're exactly the same. So you could say that the vector that goes from p to q is u. If you want to talk about the vector that goes from q to p, that's just going to be u in the opposite direction, all right? So we could write that as negative u. If you want to look at qr, the vector that goes from q to r, well, you see vector v right here, so this is vector v as well. But if you multiply by 2, then you've got the vector that goes from q to r. So you could write qr as 2 times v. And then finally rs, the vector that goes from r to s. And notice that this vector rs is going to be parallel with u, but going in the opposite direction and 3 times as long. So you could write rs as negative 3 times u. Okay. And now here's a much better picture than what I wrote here for part B that basically reiterates the same thing. Okay. All right, moving on here. Now, vectors are extremely useful in studying motion and forces. Now, regarding motion, one good example of how we can use vectors to study motion is whenever you have some particle moving through a moving medium, like air or water. Because you have the particle moving in a straight line in one direction through the water. But if it is in a direction that's opposite, or no, not opposite, but at some angle to the direction of the water, then the direction of the water is going to influence the overall direction, meaning the direction relative to the ground. So the direction of that particle, whether it's an airplane or ship or whatever, the motion relative to the ground is just going to be the velocity relative to the air together with the velocity of the wind. So you could have the airplane that is pointed in this direction and flying in that direction relative to the air, but then you have the wind direction in this direction. And then you add those two vectors together to give you this red vector, which is going to be the sum of the motion of the plane and the motion of the wind together, which will then give you the resulting vector, the velocity relative to the ground. Or you just sum up the velocity relative to the air, which is the v sub a, plus the velocity of the wind. So, hey, this is an equation. This is an equation. So if you know any two of these three vectors, then you could solve for the third vector. So if you know the velocity of the plane relative to the ground and the wind speed and direction, then you can calculate the velocity relative to the air, for example. Or if you know the velocity relative to the ground and velocity relative to the air, then you can find the velocity of the wind. Okay. All right, so let's take a look though how do we actually add two vectors? Well, vectors are, perfectly good objects, and just like numbers, we can add them. Now, we can't do everything with vectors that we could do with numbers. For example, it doesn't make sense to divide one vector by another vector, but we can certainly add two vectors. So here's how we add two vectors, geometrically at least. So we have a vector v here in the black, and then we have a vector u here. And how do we add them? Well, there's actually two ways, and they are perfectly fine. Some people prefer the triangle rule. The triangle rule basically says is that you put the two tails together of u and v, like you see here. Here we put the two tails of u and v together. Actually, no, I'm sorry. No, we went from head to tail. Here's vector u, and here's vector v. So we put the tail of v to the head of u. And then the resulting vector of u plus v is going to go from the tail of u to the head of v. So here's u, here's v, here's u plus v. All right. Now, with the parallelogram rule, that's where you put the two tails together. And you have the tail of u, so there's u, here's v. And then what we mean by parallelogram is that you will then see that u and v form adjacent sides of a parallelogram. So sketch a line segment that's parallel with u. So there's your line segment parallel with u, and a line segment parallel with v to complete the parallelogram. And then the vector that goes from where the two tails met out to the opposite corner of the parallelogram, then that vector is u plus v, which is equivalent to the triangle rule. So you could use the triangle rule or the parallelogram rule. The triangle rule and the parallelogram rule are equivalent in geometrically adding two vectors. Now, if you need to take one vector minus another vector, u minus v, you can kind of think about u minus v as u plus negative v. So imagine that you've got a vector v right here is the black one, and vector u is the blue one. And what does u minus v look like? Well, using the triangle rule, you can put negative v with the tail of negative v at the head of u, and then u plus negative v will take you from the tail of u to the head of negative v. So here's u minus v right here. Otherwise, hey, you've got vector u, you've got vector v, and then u minus v is going to go from the head of v to the head of u when you put the two tails of u and v together. All right, so let's just repeat that. U minus v, when you're finding it directly, you put the two tails of u and v together, and u minus v will go from the head of v to the head of u. Okay, moving along here, let's take a look at example number 2. And this will be on page 780 of the textbook. So what we need to do is take a look at the picture that I'm going to show you here in a minute, and to write the following vectors as, and we're going to write OP, for example, in terms of the vector u and the vector v and the vector w that they're going to show us here in the next slide here. Part B here, OQ, and part C, QR. All right, so we're going to find these three vectors in terms of vector v and vector w. All right, so let's take a look here. This is the picture that they're showing us, figure 12.10. Now, for part A, they want us to find OP, the vector that goes from O to P. Now, O is right here. So the vector that goes from O to P would be this one here. Now, you can kind of think about taking vector v and multiplying it by 3. So you have 3v here. And then taking vector w and multiplying it by 2. And then adding them together by the parallelogram rule, and you have 2w plus 3v. For example, now let's take a look here. Here's a much better picture of what I just did, but this time they use the triangle rule. All right. For part B, here's the vector that goes from O to Q. All right, here we've got the negative of W, and we've got 3 times the length of V. So we have 3V, and then you add them together, you've got 3V plus negative W. In other words, 3V minus W is how you can write OQ. All right, moving along here. Now for QR, here's the vector that goes from QR. How can we write QR in terms of U and V? Well, here's V and W. So if we go from Q rightward 1 unit on this grid, hey, that's just v. And that's all we need to do to get the rightward movement. And then you go 2 times v up in this direction here. And then you add them, and you got v plus 2w is a way of writing qr. Okay? All right, moving along here. Now, let's talk real quick about a position vector. Now, a position vector is something like this. Now, imagine that you've got the xy plane, and we've got some point out here on the plane with coordinates v1 and v2. And we're thinking about the vector with the tail at the origin and the head out here at the point. Well, then the position vector that goes from the origin out to this point is going to be written like this, v1 comma v2, using angle brackets, not the parentheses that we're used to indicate the coordinates of a point. We're talking about these angle brackets, which indicate the position vector that goes from the origin out to v1, v2. All right, so there's your position vector. Alternatively, we say that the vector is in standard position where the tail is at the origin. But remember, use the angle brackets to indicate the vector. You know, we say that v1 and v2 are the components. v1 would be the x component, and v2 would be the y components of the vector. So we could say this vector v here. So v1 is the x component of vector v. v2 would be the y component of vector v. Why? Well, so to speak, that if you were to just drop a perpendicular from that head of vector v down to the x-axis, all right, then the length of this line segment from the origin horizontally out to where that line, where that perpendicular hits the x-axis, that would have a length of v1. And likewise, when you're up here on the y-axis, you have v2, which is perpendicular. Well, which is where the line that's perpendicular from the head of the arrow out to the y-axis hits the y-axis. All right. So anyway, so moving along here. Now, all of these vectors over here you see on the right, these blue vectors are all equivalent. In fact, they're equal to vector v. They could be in different locations as long as they're pointing in the same direction and have the same magnitude, then they are all equal to vector v. It just might be, though, that we're given the coordinates of the tail and the head, and then that we have to then find the, the position vector that goes from, P to Q, for example, all right? So if we have this vector that goes from P to Q, where P is at point x sub 1, comma y sub 1, and Q is at point x sub 2, y sub 2, then the x coordinate, or the x component of PQ is right here. It's going to just be the difference in the x coordinates. All right, you see that? The difference in the x coordinates. You can kind of think about seeing this 90-degree angle right here. So the length of the horizontal displacement is just going to be the difference between the x2 and the x1. And likewise, the y component will be y2 minus y1. Just the difference in the y components or coordinates. Now, make sure, though, that you're taking the coordinates from Q at the head of the vector, minusing or subtracting the components, or the coordinates, I should say, of the point P at the tail. Make sure that you do it in that correct direction. All right, so here is how you write the components of the vector that goes from P to Q. Take the difference in the x coordinates and the difference in the y coordinates. And then if you wanted to find the magnitude, meaning the length of the vector from P to Q, then you'll just take the square root of the sum of the squares of those components, just using the Pythagorean theorem. By the way, seeing this notation right here, the two vertical bars, yeah, you can kind of think about that as absolute value. Think about what absolute value is for a real number. It just computes the distance between the point and 0 on the number line. Well, the magnitude of PQ is just the length of the vector, or the magnitude of the vector, using two-dimensional geometry. All right, so let's just summarize what we talked about here. We have the vector that goes from P to Q, where P has coordinates of x sub 1, y sub 1. Q has coordinates x sub 2, y sub 2. So you could write PQ just like this right here, x sub 2 minus x sub 1, comma, y sub 2 minus y sub 1. We could take the magnitude of PQ by using the Pythagorean theorem like this, or the distance formula. Same thing. Okay. Moving along here. Let's do an example. This is example number 3 from page 782. Given the points O at coordinates 0, 0, point P at -3, 4, and Q with coordinates 6, 5, they want us to find the components and magnitudes for these two vectors for part A, vector OP. Well, to get the x coordinate, we'll just take -3 minus 0, which is -3, and 4 minus 0, which is 4. All right, and then the magnitude of OP will be just the square root of -3 squared plus 4 squared, which is 5. So 5 is the magnitude of vector OP. All right, for part B of this example, we have the vector that goes from P to Q. Now, going from P to Q, we're going to take the coordinates of Q minus the coordinates of P. Now, we're going to go 6 minus -3, comma, 5 minus 4. So that's going to give us the vector 9, 1. And then the magnitude of PQ will just be the square root of 9 squared plus 1 squared, which is the square root of 82. Whatever that is. All right. It's just a number. Moving along here. All right. Now, we're going to now talk about adding two vectors, but using the components so that we can algebraically add the two vectors. Now, here's a way of kind of thinking about how we add the two vectors. We have vector u and vector v. Vector u has components, vector u has components u sub 1 and u sub 2, right? See here this. And we have vector v with components v1 and v2. And then using the parallelogram rule, then u plus v will take us out to here. You see the red vector. Now, notice that the x component of u plus v is just u sub 1 plus v sub 1. And the y component of u plus v is just going to be the u sub 2 plus the u sub v. Okay? So the coordinates of this point at the head of u plus v is just going to be u sub 1 plus v sub 1, comma, u sub 2 plus v sub 2. And so that means that to write the components of u plus v, it'll just be the sum of the x components and the sum of the y components. That's all there is, just adding the components together. All right? When you want to multiply by a scalar algebraically, all you need to do is multiply the x component by that scalar, multiply the y component by that same scalar. If you have that scalar to be a negative number, then that resulting vector cu will just point in the opposite direction, but the idea is still the same. You're just multiplying each of the components by that same scalar. All right, so we have vector u, which is u sub 1, u sub 2, and we have vector v, which is v sub 1, v sub 2. We want to add them to those two vectors together, add the components. You want to do u minus v, well, you subtract the components appropriately. And this should make sense because when you do u minus v, that's the same thing as u plus negative v. And if negative v would be v, but with the components with negatives in front of them. Okay, the negative of the components. Cu is just vector u where the components are each multiplied by that scalar c. All right, let's do an example. Example number 4. Suppose that we've got vector u as negative 1, comma 2, and then we have vector v with components 2, comma 3. For part A of this example, suppose that we wanted to find the magnitude of u plus v. All right, how to do that? Well, u plus v will just be the vector with the x components of 2 plus negative 1. Or negative 1 plus 2, I should say. Let me fix that real quick. So negative 1 plus 2 and 2 plus 3 for the y component. So what we would end up with is 1, comma 5. That is u plus v. And then to find the magnitude, of course, of that resulting vector, that will just be the square root of 1 squared plus 5 squared, which is the square root of 26. Okay. For part B, they want us to simplify 2u minus 3v. Well, look, 2u is 2 times negative 1, comma 2. Oops. And we're going to subtract 3 times vector v. V is 2, comma 3. Now, we have 2 times negative 1, comma 2, which gives us negative 2, 4, and then minus vector 3 times 2 is 6, 3 times 3 is 9, and that would be negative 2 minus 6 is negative 8, and 4 minus 9 is negative 5. Okay, so negative 8 comma negative 5 is what 2 times vector u minus 3 times vector v is. Okay? Moving along here. Now, it'll be convenient for us to deal with unit vectors. And what a unit vector is nothing more than just a vector of length 1 or magnitude 1. We oftentimes will use a hat over the vector to indicate that it's a unit vector. So we might have I hat here, which, by the way, happens to be a very basic, fundamental unit vector that points in one unit in the direction of the x-axis. And we have j hat here, which points in the direction of the y, the positive y-axis. Just one unit. These happen to be called coordinate unit vectors, I hat, j hat. But whenever you see a hat over a vector name, that means it's a unit vector. All right, so unit vectors are nothing more than vectors of length 1. So we will oftentimes then express vectors as some linear combination of those coordinate unit vectors. So we could have vector 3, 4 that you see here, for example, as 3i hat plus 4j hat. Think about 3i hat is, well, here's I hat. So 3i hat will just give you this vector right there. And j hat is just one unit in the positive y direction. So 4j hat will take you up to here. So you add those together and you got 3i hat plus 4j hat, which is exactly the same thing as component 3, 4. And in general, if you have vector v1, v2, you could write that as v1 I hat plus v2 j hat. Just two different ways of expressing the same vector in component form or using coordinate unit vectors. Now, from time to time, it'll be convenient for us to unitize a vector. Now, what we mean by unitize is to find a vector of length 1, in other words, a unit vector, pointing in the direction of our desired vector. So, for example, suppose that we've got some vector v, the black vector here, and we want to find a unit vector that points in the direction of vector v. So what we do is we take vector v and divide by its magnitude. Now, remember that the magnitude is just a number. And then you take the reciprocal of that magnitude is just a number. So when you multiply vector v by the reciprocal of the magnitude of vector v, you're just multiplying vector v by a scalar such that the resulting vector will be a unit vector. Either in the positive direction, meaning in the direction of u, or in the opposite direction of u. If you want a unit vector in the opposite direction of u, then just put a negative in front of v over magnitude v. Okay? So, if you want to unitize your vector v, then just take vector v divided by its magnitude. And then plus or minus, and you'll have two vectors that are parallel with vector v. And then if you want to have some vector of any particular length, like length c, in the direction of v, well, then what you'll do is you take v, divide by magnitude of v to make it a unit vector, and then multiply by c. And then you'll have a vector of length c in the direction of v. Ta-da! And then, of course, put a plus or minus in there to give it the direction that you want, either in the direction of v or in the direction opposite of v. So let's do an example. So suppose that we've got point P, 1, -2. And we have a point Q, 6, 10. Now for part A of this problem, let's try to find PQ, which we know how to do, and then 2 unit vectors parallel to PQ. Now PQ, all right, so if you remember how to do this, we're going to focus on the x component first, 6 minus 1, comma, and then the y component, 10 minus -2. So this will give us 5, 12. And then we need to find the magnitude of PQ, which will be the square root of 5 squared plus 12 squared. All right, so that's 25 plus 144, which is 169. Square root of 169 is 13. So the magnitude of PQ is 13. And then a vector that is of unit length but parallel with PQ then will be PQ divided by magnitude PQ, which means that we take each of the components of PQ divided by 13. So we have 5/13, 12/13. In fact, plus or minus will give us 2 unit vectors, one in the direction of PQ, the other one in the opposite direction of PQ. Okay? Now, for part B of this problem, we are being asked to find 2 vectors of length 2 parallel to PQ. So if you want a vector in the direction of PQ, but of length 2, then just take 2 times PQ divided by magnitude PQ. Now we've already got PQ over magnitude PQ. So all we need to do is just take, in fact, let's do a plus or minus in front of that because they want 2 vectors. So we'll do plus or minus 2 times 5/13, 12/13. And so we'll have plus or minus 10/13, 24/13. So we have positive 10/13, 24/13, and we have negative 10/13 and negative 24/13 as our 2 unit vector, or not, I'm sorry, not unit vector, but vectors of length 2 that are parallel with PQ. Moving on here. Now, vectors themselves are a kind of like a universe, or what we call a field of objects that obey certain algebraic properties. And here's kind of a laundry list of all those properties that vectors obey, and I'll just run through these real quick. U plus V is equal to V plus U. That basically says that vectors obey the commutative property addition. It doesn't really matter what order that you add the 2 vectors together. The same thing with the real numbers. Same thing for the associative property of addition. If you're going to add 3 vectors together, you can add the first 2 and then the third, or you could take the first plus the sum of the second and third. All right. Now, there is the 0 vector, and if you add the 0 vector to any other vector, that won't change that other vector. So any vector plus the 0 vector is the same vector. Any vector plus its negative is going to be the 0 vector. Some scalar times the sum of two vectors will be the same thing as the sum of the scalar multiples of those two vectors. Or if you have the sum of two scalars times the vector v, that would be the same thing as the sum of each of those scalars times the vector individually. The scalar 0 times any vector will give you the 0 vector. Some scalar times the 0 vector is going to give you the 0 vector. The scalar 1 times any vector will give you the same vector. If you have some scalar times some other scalar multiple of vector v, that would be the same thing if you were to multiply those two scalars together and then multiply by vector v. All right, so now that we've gone through those formalities, let's do something a little bit more interesting where we could solve some practical problems. Now we're just going to go through two examples, actually three examples here, example 6, 7, and 8. All right, so remember that we use vectors to sort out the velocities of some sort of particle or object going in a straight line through some medium that is flowing at some angle to the path of your object. Now let vector VW be the velocity relative to water. We're going to focus on a boat going down the river, but not necessarily downstream. So VW is the velocity of the boat relative to the water. Now vector W is going to be the velocity of the water. So your boat is headed this way in the water. The direction of the water is according to the blue arrow. But if you are an observer on the shore, then the red vector will be the direction that the boat appears to be going. Okay? But in order for you to go in the direction of the red vector, you need to steer your boat in the direction of the black arrow. Now V sub g is going to be the velocity relative to the shore. VW is the velocity relative to the water. W is the velocity of water. And of course, the sum of V sub W plus W will give you the V sub G. It's an equation. If you know any two of the vectors, then you could solve for the third one. All right, so let's now take a look at example 6. Assume that the water in a river flows southwest, 45 degrees west of south. All right, so maybe it looks something like this. 4 miles per hour. Okay. So then we have the boat traveling due east at 15 miles per hour. So this angle right here will be 45 degrees. Right here. But this is relative to shore. So this vector right here is V sub G. And this vector here for the water, that's your vector W. So what we need to do now is solve for V sub W. We're supposed to find the speed of the boat and its heading relative to the moving water. So we need to find V sub W. Okay? Now, V sub W, because of the fact that V sub G is equal to V sub W plus W, that means V sub W will be equal to V sub G minus W. All right, let's put little arrowheads over the top of all these guys. Okay, so now V sub G, here we could write this as V sub G, we could write this as 15, 0. Now, W here is pointing in the direction of 45 degrees to the southwest with a magnitude of 4. So we could write W as, let's see here, -2 times the cosine of 45 degrees, which is 1 over square root of 2. And we could also write the y component of W is -2 times the sine of 45 degrees, which would be 1 over square root of 2. So there's W. All right, so now, so what we're going to do now is find V sub W. V sub W is V sub G minus W. All right, so that's going to be 15, 0 for V sub G minus W, which is -2 over square root of 2, comma, -2 over square root of 2. So that will be 15 plus 2 over root 2, comma, and 2 over root 2. So actually V sub W should be up here, huh? Because we're doing V sub W being equal to V sub G minus W. So here's minus W up here. And V sub G plus minus W will be up there. All right, so never mind this guy right here. All right, so this would be V sub W up here. All right. Anyway, now to find the speed, then relative to the shore, we just need to take the magnitude of V sub. No, not relative to the shore, but relative to the water, I should say. The speed relative to the water would be the magnitude of V sub W. So square root of quantity 15 plus 2 over root 2 squared plus 2 over root 2 squared. And that works out to be approximately 18, as in 18 miles per hour. Okay. Now, if you want to find the direction or the heading, then all you need to do is just take the arc tangent of y over x, or the arc tangent of the y component over the x component, which would be 2 over root 2 over 15 plus 2 over root 2. Well, then let's go ahead and do that. I've got my graphing calculator, and here's my graphing calculator. Now, let's make sure that we are in degree mode. So I'm going to put my calculator in degree mode from the mode menu. And then I'm going to find the arctangent button. There we go. All right, now hold on here. I need to fix something. I've just come to understand that, and it's okay, we make mistakes sometimes. I gotta fix this though. For W, this is going to be negative 2 root 2, because we took 4 times 1 over square root of 2, which would give you 2 root 2. So the x and y components of W would be negative 2 root 2 for both of those. Okay, so let me just fix that real quick. I've got my handy little eraser here, and that's one of the reasons why I like for people to do their math work in pencil, recognizing the fact that we're going to make mistakes. Even the best of us will make mistakes from time to time. I made my share of them, and I'll probably make many more. And I'll be the first one to admit it. No shame in doing that too. So just go ahead and fix our little mistakes here. So this will be 2 root 2, 2 root 2. Now let's go ahead and calculate that angle. Okay, now we have 2 times the square root of 2. And then we're going to divide that by quantity 15 plus 2 root 2. Close parentheses, close parentheses. And that gives us about 9 degrees. So 9 degrees heading on the water with a speed of 18 miles per hour, together with a direction of the water at 45 degrees to the southwest, and water speed at 4 miles per hour. Those two motions will combine to make motion of the boat relative to the shore 15 miles per hour going due east. Okay? Alright, so check that out. Make sure that you can work through a similar sort of problem. Just rework this problem on your own, and you'll be successful for similar problems on the homework, as well as future quizzes and exams and stuff. Alright, so here's a good picture of what it is that we just talked about here. We were given the red vector and the blue vector. The red vector was the motion relative to the shore. The blue vector was the motion of the water. And we needed to find V sub W. All right, moving along here. Now, we could use vectors to analyze forces. Now, here we've got a picture of a boy applying a force to the wagon by pulling on this handle at a certain angle theta. So we have force applied at a certain angle. So relative to the ground, which we associate with being horizontal, then we could break this down into horizontal and vertical components. We have the x component of the force being the magnitude of the force times the cosine of angle theta, and the y component of the force being the magnitude of F times the sine of theta. So you can kind of think about vector F as being broken down into horizontal components. Okay. All right, so moving along here. So we can then take a look at example 7. Suppose that we have a child pulling a wagon with a force of 20 pounds magnitude at an angle of 30 degrees with respect to the horizontal. So we've got this picture right here. So then we can take the magnitude of 20 pounds times the cosine of 30 degrees. And 20 times the sine of 30 degrees to give us the y component. Sorry. Now, cosine of 30 degrees is square root of 3 over 2. So we could write f as 20 times the square root of 3 over 2, comma, and then the y component would be 20 times the sine of 30 degrees. Sine of 30 degrees is 1/2. So we've got this vector, see, 20 times the square root of 3 over 2, that's 10 times the square root of 3. And then we have 20 times 1/2, which is 10 for the y component. So this vector right here, 10 root 3, comma 10, is your force vector. Okay? All right, let's just do one last example here where we can use vectors to analyze force. Now this scenario here, we've got this heavy object, in this case an engine, being suspended by these two chains. Now these two chains could be attached to the ceiling at any angle. This just happens to be a fairly simple problem in that the two chains are of equal length. So that means that these two angles are going to be the same. In this example, those two angles are 60 degrees each. Now, suppose that we know that that engine is 400 pounds. Can we find the tension on the chain? And what do we mean by tension? The tension is nothing more than the magnitude of the force being applied to the chains. Now, suppose that we just analyze the forces. So we have this little free body diagram where we have this downward force. We're calling it F sub 3 to indicate 400 pounds. We can even write this as negative 400 j hat, for example. And then we have F sub 1, we have F sub 2. Because of the fact this engine is not moving, then the sum of the three forces will be equal to 0. So we have F sub 1 plus F sub 2 plus F sub 3 being equal to 0. Right? Just, one of Newton's laws says that an object at rest is, stays at rest unless some sort of force is applied, in which case it would be accelerated. All right, but this is not moving, so the sum of the three forces is equal to 0. Now we know what F sub 3 is, but we're going to have to then find F sub 1 and F sub 2. Now, because of the fact that those angles are the same up here, 60 and 60, that means F1 and F2 are really going to turn out to be the same. So we're just going to kind of go through and solve this problem by setting up a system of equations. So let's take a look at this picture right here. Now, F sub 1 is the force for this chain on the right. All right, so this vector is going to point upward to balance out the F sub 3, which is pulling the engine block downward. Now, because this angle up here is 60 degrees, that means that this angle down here is 60 degrees. All right, so what we'll then do is take magnitude of f sub 1 times the cosine of 60 degrees. That'll give you the x component of f sub 1. And take a magnitude of f sub 1 times the times the sine, I should say, the sine of 60 degrees to give you the y component of f sub 1. And then likewise for f sub 2 over here, take f sub 2 times the, cosine, but this will be in the negative x direction. So we have a negative magnitude f sub 2 times the cosine of 60 degrees. And then magnitude f sub 2 times the sine of 60 degrees for the y component of f sub 2. All right, so now what we do is we're going to, again, take f sub 1 plus f sub 2 plus f sub 3 and set that sum of forces equal to the 0 vector and solve for magnitude f sub 1 and f sub 2. So let's go ahead and do that. All right, so f sub 1 plus f sub 2 plus f sub 3 is equal to 0 because the engine is at rest. Now, what is f sub 1? F sub 1 is magnitude f sub 1 times the cosine of 60 degrees, comma, and this needs to be an opening angle bracket, and then magnitude f sub 1 times sine of 60 degrees. So there's f sub 1. F sub 2, negative magnitude f sub 1, don't forget the vectors there, times cosine 60 degrees, comma, magnitude, that's supposed to be f sub 2 there, magnitude f sub 2 times the sine of 60 degrees. And then plus f sub 3, which is going to be 0, comma, negative 400. That's equal to the 0 vector. All right, so you add up the x components. You have magnitude f sub 1, cosine 60 degrees, that's this guy right up here, plus this x component minus magnitude f sub 2, cosine 60 degrees equals 0. All right, and then the y components, magnitude f sub 2, sorry, f sub 1 I should say, let me fix that real quick. Magnitude f sub 1, which is this guy right up here, times the sine of 60 degrees, plus magnitude f sub 2 times the sine of 60 degrees, and then minus 400 is equal to 0, so I'll say that this is equal to 400. Now, we have two equations with two unknowns. Now, from this first equation, you've got magnitude f sub 1 minus magnitude f sub 2. And if you factor out the cosine 60 degrees, that's equal to 0. Now, using the zero factor property, cosine of 60 degrees is not equal to 0. That means that magnitude f sub 1 minus magnitude f sub 2 is equal to 0. In other words, magnitude f sub 1 is equal to magnitude f sub 2. All right, so that's nice to know. In fact, we were already guessing that. But what exactly is the value of either one of those? Well, then what we could do is we could substitute magnitude f sub 1 and for magnitude f sub 2, or vice versa, into the second equation. In which case, if you, for example, to substitute f sub 2 in for f sub 1, then you have magnitudes thereof. Then you have both of these terms would be the same. Then you'd have 2 times magnitude f sub 2 times the sine of 60 degrees is equal to 400. Divide by 2. And by the way, sine of 60 degrees is square root of 3 over 2. 2 times the square root of 3 over 2 is just square root of 3. So you have square root of 3 times the magnitude of f sub 2 is equal to 400. So that means that magnitude of f sub 2 is equal to 400 divided by the square root of 3. And since up here we found that the magnitude of f sub 1 is the same thing as magnitude of f sub 2, then that means that the tension on both of the chains is going to be whatever 400 divided by square root of 3 pounds is. Okay? And I guess that works out to be about 231 pounds, about 231 pounds of tension. All right? Now, we're going to do a much more complicated problem involving 3 chains in 3 dimensions or something like that when we get into section 12.2. So it's kind of imperative for you to master this in preparation for the next section. All right, so when we get into section 12.2, which is my next lecture, we will talk about vectors in 3 dimensions and then how to combine them using, of course, addition and subtraction, scalar multiplication. But in a future section, we'll talk about the dot product and the cross product, which are 2 different ways of actually multiplying 2 vectors together. We'll also talk about some topics from 3-dimensional geometry in section 12.2 as well. So, for example, the 3-dimensional coordinate system, x, y, and z axes, distance between 2 points in 3 dimensions, and equations of spheres and stuff like that. So, good times ahead. All right, I'm going to be done with this now. You have a good night, and I'll see you tomorrow. Okay? I'm going to have to stop recording here.